Hi everyone, and welcome to our first installation in our DC machine series. By now you should have already looked at the the 3D model video where you could see the construction and basic operation of the machine. If you have not looked at that, go and look at it now before we get into the mathematics and so on. It will help you clear up the whole concept of the operation of the machine a lot more with the 3D, being able to see the 3D visualizations. Um, and by the end of this session, I hope you will be able to describe the construction and operation of a DC machine and derive the armature, EMF, and torque of a DC machine. So to get started, we're going to cover some basic terms that you'll come across, not only for the DC machine, but for all the machines. We have mechanical terms such as the rotor, which is the rotating part, and the stator, which is the stationary part. So rotor rotates, stator stays. So the rotor again is the part that rotates. It is usually on the inside, and the stator is the stationary part. This is usually on the outside. So in addition to that, we have some electrical terms that we would hear that are sometimes used interchangeably, but you really shouldn't use them interchangeably. We have the armature, which is the power carrying component of the generator or motor. This is the part, these are the windings that take power from the source and transfers it to the load. And then we have the field winding, and this winding simply creates a magnetic field so that the field from the armature has something to interact with, and it is the interaction of these magnetic fields that allow us to produce torque in the machine, as we will see, and as you should have done in ECNG 1015. So for the DC motor, we have the stator on the outside, and the rotor is this part on the inside. The field winding in this case goes on the stator, while the armature windings go on the rotor. So we have the field windings here connected across here and here, and that produces an a magnetic field. In essence, this is a giant electromagnet that you stick the rotor into. And as we can see, when we have a current carrying conductor, so we have our source here, and the current goes up into the windings and then comes back. We have a magnetic field with a current carrying conductor in it. Then it will experience a force, and the direction of that force is given by Fleming's left-hand rule. So if you point your second finger in the direction of the current, which is this way, and your first finger in the direction of the magnetic field, which is this way, then your thumb finger, if stuck up, should go in the direction of the movement, the direction of the force. So on this side of the winding, we'll experience an upward force, and then on this side of the winding, we have the current coming the other way. The current comes down, so we have the direction of the field remains the same. The direction of the current changes, and now we will get, so we have the field this way, the current this way. Oh, let me draw it like this way, and then the force would be down. So this is the direction of the force. It is upward in this case and downward in this case. So you get a rotating force as shown here, one side going up, one side going down, and that is how we create torque. Now what about these sections here? This section is not perpendicular to the magnetic field, so you would not get any force on this section of the winding. And of course, the force, when it is in a rotating system, a rotating force, we call it a torque. So force and torque is the same thing, except torque refers to the force when it is rotating. A rotating force is a torque. Now, one of the problems is if this conductor, let me take off here, if the conductor on this side, this conductor here, if this conductor goes over to this side and then the current is still, say, in the same direction, if it was in this direction still, so if I just rotate it but the current was going in the same direction through the winding, then when the current was on this side, it would experience a force going upward. So what would happen is the winding would go to this side and then the direction of the force would be reversed, so it would go back to this side. So it would start oscillating. So what we have to ensure is that the winding, whichever winding is on this side, the current is always in this direction, and when the winding comes on this side, it goes in the opposite direction. So in order to do that, we have to reverse the current flow through the winding. So the way we accomplish this is by what we call a split ring commutator. And we'll see how that works now. So we have our power source and we have these rings. It's essentially a ring that is broken in the middle. So they are not connected to each other. So when we have the rotation of the winding on the inside, and let's see which direction it should go, field, current, and then motion should be upward. So this one would experience an upward force and this one a downward force. As it turns, so now remember the current goes this way and then comes this way. As this turns, this is side 1, this is side 2. When side 1 goes over to this side, then the current would go into side 1 and up this winding, which would now be on the other side. So let's look at it progressively. We have in one case winding 1, winding 1 prime. This is the winding, this is like this winding here, 1, 1 prime. And we have our brushes and our commutator. So when the angle is 0, this is our angle here, this is our field, and we are taking the angle at 0 as this orientation of the commutator. So when it is at 0, I have current going into 1 and coming out of 1 prime. Now as it goes to 90 degrees, so now we have the break on this side. What happens is I have both of them shorted together, which means there's no voltage across it and hence there would be no current. And then when it goes over 180 degrees, so now we have 1 on this side as opposed to this side, then I have again the commutator separated. So I have now current going into 1 prime and coming out of 1. So before, the current was going into 1 and coming out of 1 prime. The current is still going on this side, on the left hand side of the winding. The current goes in all the time, and on the right hand side the current comes out all the time. So we switch the direction within the winding by having this break in the conductor. And what that creates now are these areas of zero torque. So we have we have the winding starting off. This was when the angle is 0, and as the angle increases, at some point in time, the two contactors, the two sides of the commutator meet, and when the commutator meets, so that is when the breaks come here and here, when that happens, then the winding is shorted, you get no current, so you have no voltage across 1 and 1 prime, and no current from 1 to 1 prime. And then when it crosses the gap, you have the current going the other way. So instead of going into 1 and coming out of 1 prime, it goes into 1 prime and comes out of 1, and then the contactors, the gap is reached again, and the windings are shorted, and then it reverses. Now this is the graph for the voltage from 1 to 1 prime and the current going through 1 to 1 prime. The voltage across the brushes, though, if I were to draw this voltage here, EA, if I were to look at that voltage is always in one direction. The only time the voltage drops is when the contactors, when we have the gap reaching the brushes, and then it short circuits temporarily the supply. So in that case, EA will drop to 0, and then when it crosses again, it will come to whatever is the DC value here. And similarly, the torque does the same thing. So the problem this creates if we just have one break in the winding is that we get this pulsating torque, and that is not something we want. And you'd have seen this in the video as well. So this pulsating torque is not something we want. We want the machine to run smoothly. So what we do is we add on additional segments in the commutator. So if we look at this now, this is our DC supply with our brushes. Now in this position, we will have current coming through here, down through this winding, and going like this. And we'd also have current coming through here into this winding like that. So that is how we end up with this circuit. Two windings energized on this side, two windings energized on this side. So all the windings are energized, and we're going to have the maximum torque we could get. Now, when we reach a break in the circuit, what we have is this will become short-circuited, so this winding is not energized. These two are short-circuited, so this winding is not energized, but I still have a break from the top to the bottom. So the current could go like this and like this. So I have two windings being energized while two windings are short-circuited. So in this case, if the windings are all equal, if they're all identical, I should get half torque dip only. So what I see now is by increasing the number of segments, so you could imagine this is for 4, as I increase that number of segments, then what is going to happen is this is going to get shallower. But notice that now I have 4 breaks because we encounter a break every 90 degrees, 90 degrees, 90 degrees, 90 degrees. Whereas before, I was encountering a break every 180 degrees. So what I end up with here is more areas of discontinuity, but each discontinuity creating a smaller disturbance. So both the torque and the EMF pulsations are reduced by increasing the number of the commutator segments. Sorry, this should be commutator segments. Good. So how are these? So we've looked at how the commutator is organized, how it is arranged. Now there are two ways in which we could connect the windings to the commutator. I'm not going to spend too long on this. I uploaded a document from IIT Kharagpur, and you could look at that for a much more detailed explanation of the windings. But basically, we could wind the machine, the armature, in two ways. One way is what we call a lap winding, and this way basically we put the windings, the conductors, in parallel. So you see here all the little conductor loops, they lap each other, so they're called lap windings. And this shows you here on the bottom here, this is the commutator segment. If we unroll it, and these are the winding, this is how the windings actually proceed. So you have the winding coming here and then coming back to the immediately the next position, and then you continue like that with progressively lapping the winding as you go around. And the other way is to do what we call a wave winding. In this case, you don't bring back the winding to the next adjacent one. You just keep wrapping it around like this in a wave. And remember, this is a circle, this is a commutator, so you end up with the same amount of conductor. It just goes progressively around the winding. But if you look at that document, you'll see a very detailed explanation of how you calculate what these spacings are supposed to be with respect to the number of poles in the system, with respect to the number of commutator segments, and you'll see exactly how the windings are laid out. So that is a little bit beyond the scope of the course, but you should go through it if you want to have a very good idea of how the machines are constructed, how the windings are constructed. Now, in essence, this is like a series versus parallel combination, and why we need to know lap winding and wave winding is because we have to, they come into play when we try to calculate the back EMF of the machine. So, or what we call the armature EMF. So, the equation for armature EMF is given here, and you'll see the terms: phi, the flux per pole, the number of poles, N is the rotational speed in RPM, revolutions per minute, Z, the total number of active conductors on the armature, and A is the number of parallel paths in the armature winding. And this is where lap winding and wave windings come in. For a lap winding, the number of parallel paths is equal to the number of poles, and for a wave winding, regardless of the number of poles, the number of parallel paths is equal to 2. So that is something you have to know. So when you calculate this value, you put in the correct value for A. So let's see how we actually develop this equation. The flux cut by one conductor in one rotation is phi, which is the number of pole, the amount of flux per pole by the number of poles. So flux per pole by pole is total amount of flux. The flux cut by one conductor in n rotations would simply be multiplying that by n. And the flux cut per second would be the number of rotations divided by 60. Remember, this is rotations per minute. So divide by 60 gives us rotations per second. The number of conductors we have in series is Z on A, which is the total number of active conductors over the number of parallel paths. So if we have a set of conductors, if I have a set of conductors, I have here 6 conductors, and I have 3 parallel paths, 1, 2, 3. So this is equivalent to 2 conductors in series. So that is the number of conductors in series, total active conductors over number of parallel paths, and then the flux cut per second by the number of conductors in series will be given by this multiplied by Z on A, and that is how we derive the full equation, something that you should remember. So EA, we have phi, which is the armature voltage, is phi NZP on 60A. Now I know if I want to change this from N to omega, because omega is what we work with when we talk about torque, then I simply multiply. I know omega is equal to 2 pi n multiplied by 60. This is simply a conversion from RPM to radians per second. Or on the other hand, n is equal to 60 by omega m on 2 pi. I substitute this in here and I end up with this equation. And when I look at it, I will see there are a set of constants there. So I could take out this and all of this and just call it Ka. These are all constant things. They don't change in the motor. The motor has a certain number of active conductors, a certain number of poles, A depending on lap winding or wave winding. These are all dependent on the construction. So phi and omega m are the things that could change. At rated values, phi could also be constant. This is the amount of flux determined by the field winding. So that could also be constant, and sometimes you'll see that incorporated into the constant as well. So we have EA is equal to Ka omega m. So this is one of the equations you have to know. So you get Ka phi omega m. Sometimes you'll get EA is equal to Ke omega m, where this is incorporated into your Ke. So now that was the armature reaction. So if I had to draw the equivalent circuit for the DC motor, I have my voltage, my terminal voltage, and this is just supplied by a battery. And then I have some resistance of the windings and so on. And then I have my motor, which gives me some back EMF. So this is the basic equivalent circuit. Now if I wanted to find the power in this motor, this is EA, which is the voltage across here, multiplied by IA. This is the normal way we do power in DC circuits. P is equal to VI. P is equal to VI. In this case, we call VEA. So P is equal to EAI. And this EA is the armature reaction voltage that we just calculated here. So I know EAIA, which is the electrical power, is equal to TE by omega m. This is basically power is equal to force by velocity. Since we're in a rotating system, angular force, which is torque, by angular velocity, which is omega. So power, we have an equation for power here, and then I could substitute my values for EA. So I know EA is equal to K phi omega m, so I could substitute that in, and I get EAIA is equal to TE omega m, and I will get that being equal to Ka phi omega m IA. So if I cancel these omegas now, I will get TE is equal to Ka IA. So these are two important things. TE is equal to Ka IA, and EA is equal to Ka phi omega m. So the armature voltage is dependent on the speed of the machine, and the torque is dependent on the current of the machine. But both of them use the same motor constant because that is dependent on the construction of the machine. And this is something you will see a lot, torque being related to current. Because if you have a fixed voltage, if you think about it, if the terminal voltage is fixed, then the power is proportional to the current, and that is why we relate torque to current. So this is also the torque factored. This is the torque before we factor in losses due to friction and windage. It is what we call the electromagnetic torque. That is what the E is for. The total mechanical torque that will be available you would have to subtract the losses, the mechanical losses such as friction and windage, not windage. Has nothing to do with the windings. This has to do with the wind, the air. So friction and windage, this is just the air resistance when the thing turns, which is also a kind of friction. When we subtract those, which are drag forces, we will get the net torque which is available to the user, and that would be the torque which is specified on the nameplate or in the ratings of the motor. So we have now, if we try to develop the defining equation for the system, I could simply look at this as a series circuit. So I know VA, which is sorry, this should be VT. VT is equal to IARA plus EA plus L di dt. Where's that L di dt? So remember, we have inside the winding, we have coils of wire on the armature. So these windings, because there would be some inductance associated with it, every time you cross the commutation point, even though it's a DC machine, every time you cross the commutation point, remember we had those little dips in current. We would have these dips in current. So every time you have those dips in current, that is a di dt, and that would mean you have some voltage drop due to the change in current. But since that occupies only a very small space of time, in the steady state operation, once it is in the normal operating region, it is not breaking those commutator segments, it is not crossing a gap, then what you have is di dt going to 0 because it's a DC, and in steady state you'll simply get EA plus IARA giving you VT. And that is what basically the defining equation for the DC machine. Now if you had a series wound machine, which you'll see in the next lecture, then you'd have the field winding also being here, and instead of IARA you'd have IARA plus RF. But we'll come to that in the next lecture. And that brings us to the end of this first section on the construction and operation of the machine. So by now you should be able to describe the construction and operation and also derive the armature EMF and torque of the machine. Next time we'll look at some winding configurations and some equivalent circuits.